Searching an unsorted collection of 1 million elements leaves you no choice but to inspect every single value one by one. In the worst case, finding your item or proving it is missing takes 1 million comparisons. But if the data is sorted, every single comparison can tell you which half of the remaining space contains your target and which half can be discarded entirely. Instead of reducing the problem size by one element at a time, we eliminate 50% of all remaining possibilities in a single step. Consider an array of 9 sorted integers, 3, 8, 12, 17, 24, 31, 45, 62, and 78. We want to search for the value 45. We establish 2 pointers, left at index 0 and right at index 8. Our loop invariant guarantees that if the target exists anywhere in the array, it must lie within the inclusive interval bounded by left and right. Maintaining this guarantee across every iteration is what keeps our algorithm correct. To begin the search, we find the middle index between 0 and 8, which gives index 4. The value stored at index 4 is 24. Because our array is sorted and 24 is strictly less than our target of 45, the target cannot exist at index 4 or anywhere to its left. We discard indices 0 through 4 entirely and update our left pointer to index 5. The search space is now reduced to the subarray spanning from index 5 to index 8. With the left pointer at index 5 and the right pointer at index 8, we calculate the new midpoint at index 6. The element at index 6 is 45. We compare our target to this value and find an exact match. The search terminates immediately and returns index 6. In just 2 comparisons, we located our element within a space of 9 items, without ever inspecting the other 7 values. Now suppose we search the same 9-element array for the number 15, which is not present. We start with left at 0 and right at 8, checking midpoint index 4, value 24. Because 15 is less than 24, right becomes index 3. The new midpoint is index 1, value 8. Since 15 is greater than 8, left becomes index 2. The new midpoint between 2 and 3 is index 2, value 12. 15 is greater than 12, so left advances to index 3. Now left and right both equal 3, pointing to 17. 15 is smaller than 17, so right becomes index 2. Left is now greater than right, the valid search interval is empty, and the loop terminates, correctly reporting that the value does not exist. When calculating the midpoint between 2 indices, the intuitive formula is left plus right divided by 2. In languages with fixed-width integers, this simple addition introduces a critical arithmetic overflow bug. If the sum of left and right exceeds the maximum positive value of a 32-bit signed integer, the sum wraps around into a negative number, resulting in an invalid negative index and a memory fault. To prevent overflow entirely, we rewrite the midpoint calculation as left plus the quantity right minus left divided by 2. To derive the time complexity formally, observe that each comparison divides the active search space by 2. Starting with an initial size of n, after one step we have n divided by 2 elements remaining, after 2 steps n divided by 4, and after k steps n divided by 2 raised to the power of k. The algorithm must terminate when the remaining search space is reduced to a single element. Setting n divided by 2 raised to the power of k equal to 1, and solving for k yields k equals log base 2 of n. This logarithmic scaling is why searching a billion items takes at most 30 comparisons. Standard binary search stops at the first matching element it encounters, which is unpredictable when the array contains duplicates. Consider the array 2, 5, 5, 5, 8, 11, where we want to find the first occurrence of 5. When our midpoint hits a matching 5, instead of terminating, we treat the match as a signal to keep searching to the left by setting right equal to mid minus 1. Recording the most recent valid match while continuing to shrink the window allows us to cleanly isolate the exact lower bound index of any repeated value. Binary search achieves logarithmic efficiency because it requires only a consistent direction to eliminate half the candidates at each step. This means the underlying data does not actually have to be a physical array stored in memory. As long as any mathematical function or decision problem produces monotonic output, we can apply these exact same pointer invariants to search continuous domains or solve complex optimization problems. How do we structure binary search when we are searching over the answer space of a function rather than the indices of a list?